Congruence and similarity in triangles. So congruent triangles exist when one shape can become another. Sometimes they could be rotated, as you see right here. So they could be rotated, they could be flipped, or they could be a translation where you just move it. Okay. Corresponding sides have the exact same length, and they have corresponding angles that are the same angle. So all lengths and all angles are equal because they are the same shape. They just might be moved over or rotated or reflected. We will not spend a great amount of time focused on this on congruence in this unit. Similar triangles are triangles which have the exact same angle measure. Actually, I should circle same. They are the same angle measure. That's what a similar triangle is. But the side lengths may be resized, so it might not be the same size. So you can see that this triangle right here and this triangle right here on the outside, okay, they have the same angles. However, their lengths are surely not the same. The red one is much larger than the blue one. The triangles are then related by a scale factor, which is a ratio of corresponding side lengths, stating how much bigger or smaller the second triangle is through proportions. Through proportions you can solve for the side lengths. The following are similar triangles. Solve for the unknown sides. So first, we have to understand that we're being told these are similar triangles, so we don't have to question it. We're being told, and it seems pretty obvious that P would be equal to A, that B would be equal to Q, and that C would be equal to R right there. So that would mean that this side is in relation to that side. So what is the scale factor between PQR and ABC? Well, 18 divided by 12, if we divide those two, gives us 1.5, and this is the scale factor, meaning that PQR is 1.5 times bigger. So if we want to know this side length, we would take the 10 and we'd multiply it by 1.5, because it's 1.5 times bigger, and we get 15. So this length right here is 15. And the 7 here, we can take that, we multiply it by 1.5, and we get 10.5. And so that gives us the length of P to Q. Over here on triangles ABC and XYZ, again, we're told they're similar, so we're going to try and figure out what makes sense here. So it makes sense that B is equal to Y. They look almost 90 degrees. Almost, maybe not though. A here, which is the larger of the two, should be equal to the X, and C is equal to the Z in angle. Notice that the angles are equal, but the side lengths are not. So you got to do a little bit of head flipping here. But that means from this symbol right here, the degree symbol, to the double line, so degree to the double line here, we have 20 should be a comparison to 10. Should compare these two. So we know that the scale factor that relates these two is 20 divided by 10, or 2. So this second triangle XYZ is 2 times bigger. So we can take this 7 here, multiply it by 2, and we get 14. And what looks like a hypotenuse, but I don't know for sure, is 12 times 2, which is 24. So now we have the 3 side lengths. For fun, you can find out whether it's a right triangle. Simply check if Pythagorean theorem works. If 14 squared plus 20 squared equals 24 squared, then it is, in fact, a right triangle. But if it isn't, then it's not a right triangle. Okay, just some notes about notation. This symbol right here, kind of a squiggly, a wave, is used to indicate similarity. The congruent symbol is used to indicate congruence, so it's an equal sign with that wave over top. When naming triangles that are congruent or similar, the corresponding vertices must be listed in the same order. For example, if angle A equals D, and angle B equals angle E, and angle C equals angle F, then we would write this in the exact same order. So A was similar to D right here. And B was similar to E, so we have to put those letters second. And C was equal to F, which is why we put those letters third. It would not be proper to write triangle ABC equals triangle EDF, because those are not equal, or it doesn't show that it's equal. So similarly, let's imagine we have triangle ABC and triangle RST. We know these are similar, and they're stated in the correct order here. So angle ABC, a little note about that, if you have a triangle with A, B, and C, and we trace out angle A to B to C, so when we use this notation, we're talking about this angle right here, that angle that's formed when you draw that. Okay, so A, B, C. Let's make sure we get all the order right. So A was R. So we're going to start with R. B was S, and C is T in similarity. Angle BCA, well, B is S, is similar to S. And C is similar to T, and A is similar to R. So we write STR. For C, we have AB over RS. And I actually can put two different answers here. So we could put AC, so we're picking the first and the third, divided by RT, the first and the third. Okay, so we put it over RT. Or I could say BC, so taking the second and third letter right there, and divided by the second and third letter here, which would be ST. Similarly, if someone said to you, hey, triangle STR is similar to what? We would, again, rephrase. So we have STR. So we're starting with the second letter, third letter, first letter. So that would be triangle B, second letter, third letter C, and first letter A. ST. I'll leave it to you to try and figure these last two out, but I'm going to start with two different options here. Okay, so we're going to put ST would be, you could put RT over what? I want you to figure out what that is. Or ST, RT, or we could do RS. And you got to figure out what these two are right here, okay? So find out what those are and find out what this is. Okay, congruence and similarity. So I put this in here because some of you like going on in mathematics and seeing the ways that we can prove different things. Again, we're not going to go into any detail here, but if you want to prove two triangles are the same, we either need to prove they all have the same three side lengths, or that two side lengths and an included angle. So that looks like this. If you have a side, and the included angle. If they are equal, then we can actually say two triangles are the same. If we have an angle, a side, and an angle, so the side between the two angles, we can say it, or if we have AAS. Similarity, we're going to really focus in right here on angle similarity, and every once in a while we'll look at this side proportional. So angle is the fact that once you have two angles of one triangle are congruent to two angles of another triangle, then we know the triangles are similar. You only need two angles to be equal, because the third one we would know to be the same. Or we can look at proportional relationships here, where the ratio between all three sides of the triangle are the same. We'll look at an example below, I believe. Create a triangle that is similar to triangle ABC using a scale factor of, and we'll just make it 2. Make it nice and simple. So we're going to make a triangle that is similar, and I'm not going to draw it really nicely because that puts too much pressure on me. Okay, we'll call this X, Y, and Z, and that's pretty bad. Okay, so if these are equal, and I'm going to get them in the same order here, X, Y, Z alphabetically, we would know that C is equal to Z. So this right here would be 60 degrees. Because the scale factor is 2 does not mean that the angle becomes twice as big. Just the side lengths become twice as big. So to figure out this side right here, we would do 2.4 times 2, which is 4.8 centimeters. Here we take 3.3 centimeters and multiply it by 2, so that's 6.6 centimeters. And here we take 3.7, multiply it by 2, and we have 7.4 centimeters. And there's a triangle that has that relation. I want you to see this though for a second. So this is what the proportional thing has to do with. So 6.6 divided by 3.3 is equal to 4.8 divided by 2.4, which is equal to 7.4 divided by 3.7. Notice that all of these would be equal to 2, our scale factor. So when two triangles have all sides that are the exact same ratio, so either twice as big, 3 times as big, a third as big, then we would know that they are similar triangles. One more example here. Show that the two triangles to the right are similar and give reasons. Okay, so let's confirm we see two triangles. So what two triangles are we talking about? Well, we're talking about triangle. There's a big one on the outside there. So it's triangle D, B, and A, the outline. But there's also triangle D, C, and E. It's this one inside right here. And they do, in fact, seem to be similar. And so how can we prove this? Well, notice that we have parallel lines here. So I'm going to say angle D is equal to angle D in both triangles. And the reason why is simply they're the same angle. So I don't even know how to say that besides they're just the same. Of course they're equal. Okay, you have a parallel line, and that's going to be the hinter that gives us the answer here. If you put your head upside down for a second or rotate that piece of paper in front of you upside down, you'll get an F pattern right here. Notice our transversal, our two parallel lines. We know that angle E, I'm going to be proper here, so I'm going to say angle DEC, so this angle right here, is equal to angle DAB. And how do we know that? I'm going to go not so proper, we'll just call it the F pattern there. And so by angle similarity, because I have two angles equal already, I know that triangle DBA is similar to triangle DCE. I know that once I have two angles that are equal. Well, this tells us that there is a scale factor that relates these two triangles to each other. Now we just need to figure out what is that scale factor. So I want to look specifically at DC over DB. So this short length right here over the longer length right there. So notice that DC is equal to 6 and DB is equal to 14. Okay, so that's the ratio that is relating the smaller triangle to the larger triangle. So we could have 6 over 14 is equal to, and let's look at this side right here, so 3.6, so the short side of the triangle to the longer, or sorry, the large triangle, so small triangle to large triangle. And we'll call this one, we'll call it B for right now. And we're going to find out what this is. So we can use that little skill we learned earlier, which is cross multiplication. So notice that if we were to cross multiply, we'd get 6B equals 3.6 times 14. And 3.6 times 14 gives us 50.4. We can take both sides here and divide it by 6. And that will give us B equals 50.4 divided by 6, which is 8.4. So this length right here is 8.4 centimeters. I went with a pretty difficult question right away, but if you want to know what y is, then, well, y is only this short section here, so it's 8.4 minus 3.6. So therefore y is 4.8 centimeters. Did not give a lot of space for this, did I? Okay, and then I'm going to teach you guys a little trick just to figure this out. I'm going to erase this diagram altogether now, because there's something really fun in here that some of you might notice. We can solve through proportions, but we can also just see what kind of triangle this is. So did you notice that this triangle right here, that this length was equal to that length? That's an isosceles triangle, which tells us that when we're looking at the outside length here, that this is equal to this length right there. So this we know is 14 centimeters, which means that x equals 14 centimeters. And there you go, we got x and we have y. And so this is how we solve triangles solve similar triangles.